we'll start recording.
Okay, so we left off on Friday. We had just talked about how we metabolize free fatty acids through aerobic metabolism. Okay, and so what you guys need to remember out of all of this, and I will try to draw everything, right? I have a mitochondria here, okay, and then we essentially have carbohydrates, right, coming from glycolysis that will get moved into a mitochondria. And then we have free fatty acids that have come out of the blood into the muscle that are going to also get moved into the mitochondria. And so this is all happening simultaneously, okay? All happening simultaneously. And so we could spend, I don't know, right, 2 weeks talking about the biochemistry of kind of what is pushing one way or the other on all of this. But what you guys need to remember is, as long as you have at some point in the recent history eaten something that has fat in it and has carbohydrate in it, you are generally going to be metabolizing in aerobic metabolism both carbohydrates and fat. Okay. And so if we look at this particular graph, it's going to try to demonstrate to you guys the relative percentage of ATP that comes out of the mitochondria that has come from breaking down fat versus breaking down carbohydrate. Okay. And so what we see here is a percentage of VO2 max. And so this is an exercise intensity measure. Okay, so we're going to start off on the left side at basically 0% of VO2 max, or very, very low. This is rest. Okay, this is rest. You guys are sitting there right now, and assuming you've had a relatively mixed American type diet, okay, then you're going to be about 2/3 fat, 1/3 carbs, or 60-40, kind of in that direction. Okay. At lower intensities, like rest, walking, things like that, you will likely be able to derive a larger percentage of your calories that are being expended, or the ATP that you're making in aerobic metabolism, from fat. Okay? From fat. As the intensity of exercise increases, so as energy demand increases, okay, we're going to go here, right? Maybe a walk, maybe a jog, right? A brisk jog up to something that's much higher in intensity. What you will notice that our carbohydrate use is going to go up, and our fat use is going to go down as a percentage of the total energy expenditure. Okay. So as you go from rest to walking, you use more carbs, less fat. As you go from walking to jogging, even more carbs, less fat. And there will be an exercise intensity, okay, likely somewhere over a pretty brisk jog where you're doing very high intensity stuff, where a majority of your calories that you're burning are going to all come from carbohydrates. Okay. And in the next few slides, we'll talk about the why that is behind that, why that has to be the case. But this graph that you see here is a very, very old school sort of famous concept in exercise physiology. And what it denotes is something called a crossover point. Okay. There is an intensity of exercise at which the sort of use of carbs and fat is essentially equal. It's 50-50. And then over that, they cross over, and we go from more fat at lower intensities to more carbs as we go higher. Where this crossover point occurs, or what intensity it occurs, varies based upon a whole bunch of different things. Okay, we'll revisit it probably next week when we talk about aerobic training and some different things, but we can shift this one. But this is what's going on. Okay, this is what's going on. All right, so that's how we're going to be our intro into something called rate control of metabolism. Okay, so the last and probably the most conceptually difficult thing that we'll do for the entire semester is this. Okay. This is how we control which pathway is predominating and which energy substrate is predominating in aerobic metabolism. Okay. And so we're going to talk about this as rate control. So remember, okay, remember the time of the temporal organization. All metabolic pathways are on all the time. Okay. All of you are using everything right now. Okay. The pathway that predominates depends upon two things: overall energy demand, okay, and the speed of each metabolic pathway. Okay. So what this comes down to, at its very, very, very most basic concept, is supply versus demand. Okay. And so if you think of the ATP demand as a continuum that's going to go from rest, right, to, we'll just call this all out exercise. Okay. I need a little bit of ATP here, so I'll draw ATP small. Okay. As this moves up, we need more ATP, and then during all out exercise, we need lots and lots of ATP. Okay. This is the demand. And so we have to remember from a supply standpoint that we have creatine phosphate, myokinase, glycolysis, and the aerobic pathways. Okay. And so what we're looking at is, what is the sum total from all of these things that gets me the amount of ATP that I need over here? Okay. Does that part make sense? Okay. It does not matter where the ATP comes from initially. It's just there is a certain amount. Okay. The demand and then the speed at which these pathways can provide energy is going to be the thing that controls everything. Okay. That's going to be the thing that controls everything. And each pathway has multiple control steps. I said that each pathway. Several of the pathways have multiple control steps. Some of those simpler phosphagen ones only have one. Okay. And so we're going to talk through what controls the speed of each pathway, because the speed and the total amount of energy, kind of the combination of those two things, will tell us which one predominates and lets us meet energy demand. Okay. So we'll start off at the beginning. Okay. Remember, the speed of the pathways is pretty simple. Okay. Creatine phosphate, phosphagen systems are the fastest. Glycolysis is the second fastest. And then I'm calling this oxidative phosphorylation, but it's sort of Krebs and the electron transport chain is going to be the slowest. Okay. Why is this the order? It's really important that we understand the order. The order. Why is that the order? Why are the phosphagen systems the fastest?
Less steps.
Less steps. Okay. Why is Krebs and the electron transport chain the slowest? A lot more steps. Okay. A lot more steps. So that's going to play a really, really important piece of all of this. Okay. What I want you guys to start everything off with. Okay. Start everything off with. Think about, I know that I've said that all aerobic pathways are active all the time, but start off at rest. Okay. Start off thinking about rest. The vast, vast, vast majority of the energy that you need at rest is supplied by aerobic metabolism. Okay. Energy demand is low. And even though Krebs and ETC are slow, they provide enough ATP, okay, that we can generally meet that very low demand that we have at rest almost exclusively with aerobic metabolism. Okay? Almost exclusively. So that's our starting point. Okay. Everything else that we're going to go to now is going to be what happens when I go from rest to a walk, to a jog, to a sprint, to an all-out chase by a velociraptor kind of sprint or something here. Okay. As we drive ATP demand up, that's going to be a thing. Okay. So let's talk about rate control of the creatine phosphate, and for that, the same kind of thing basically for our phosphagen system. Okay. The primary thing, this will be a question on the test. Okay. The primary thing that drives an increase in the phosphagen system, and it's the same in all of the systems, that ramps up the metabolic activity is ADP. Okay, ADP. I have creatine phosphate and I have ADP, and that drives this reaction into creatine and ATP. Okay. So this is the biochemistry of everything. When we increase the concentration of something on one side of a reaction, in these redox reactions, it drives them to the right. So when ADP goes up, okay, this increases, we put more ADP in the classroom to bump into things, creatine phosphate, creatine kinase enzyme, ADP drives us to do all of this. Okay. When you go from rest to walking, you use ATP, ADP levels go up. When you go from walking to jogging, there's even more ATP turnover, more ADP. Okay. So increasing metabolic intensity increases ADP levels, which then activates the creatine phosphate pathway. For the most part, it activates all of them. But that's what's happening. Okay. This one is the simplest, it's the fastest. So when ADP begins to go up, we immediately start using it. Okay. We tend to then use creatine phosphate until it's gone. Use it up, it's gone. And when you stop exercise and you take a break, it will begin to replenish itself. Okay. It will begin to replenish itself. Okay. Now things are going to get a little complicated. And I apologize for that, but now things get a little complicated. And there are 4 control enzymes, 4 places that we control what is happening with glycolysis. Okay. Remember what I told you guys you need to know with glycolysis. It's glucose to glucose 6 to pyruvate. And then it's either going to Krebs or it's going to lactic acid. Okay. So there's an enzyme that plays a role at each one of these sort of steps as we go along. Okay. So the very, very first place we control the rate of glycolysis is with something called phosphorylase. Phosphorylase is the enzyme, okay, that splits glycogen into glucose. So it's going to help us get more glucose in. Okay. Splits glycogen into glucose. Right. You have glycogen in your muscles. You have glycogen in your liver. Okay. And so a thing to appreciate about phosphorylase and then phosphofructokinase, it's number 2, is these are what we call allosteric enzymes. And that means that the enzyme has a certain activity, and if it binds or comes into contact with other things, it can either raise or lower its activity. Okay. And so we activate phosphorylase by increasing ADP levels, by increasing calcium, and by increasing epinephrine and norepinephrine, the catecholamines, the stress hormones. Okay. So exercising or beginning to exercise raises every one of those things. So the initial response, as soon as you begin to exercise, is activate phosphorylase, break down glycogen, dump more glucose into that cell. Okay? Dump more glucose in. So while you are using creatine phosphate, we're activating phosphorylase and we're dumping glucose in. Okay. So we can begin this process because no matter what happens, breaking down that glucose is going to give us more energy, whether it ends up as lactic acid or it ends up getting that pyruvate going into the Krebs cycle. We're going to get a lot more energy than what we have with creatine phosphate. So that's our initial step. Okay. The second step is the control enzyme that gets us to glucose 6, from glucose 6 to glucose 1,6 phosphate called PFK. Okay. So it's the third step in glycolysis. PFK or phosphofructokinase is the slowest step in glycolysis. So this is the rate limit. Okay. PFK and therefore glycolysis is largely inhibited, meaning it's slow at rest because ATP, high levels of creatine phosphate, okay, high levels of citrate largely inhibit PFK. Hydrogen ions also inhibit it, so during very high intensity exercise, it's going to get feedback and it's going to get shut down, which is a problem. But generally, at rest, when we have plenty of ATP, PFK is not very active. Okay, ADP, AMP, inorganic phosphate are the primary things that activate it. So again, ADP. So we're dumping more glucose in. We're activating PFK with ADP. That then moves more of that glucose down through glycolysis towards pyruvate. Okay. So you start exercising, break down glycogen, dump the glucose in, activate PFK, move even more glucose on that way towards pyruvate. Okay. So at rest, PFK is largely inhibited. During very, very high intensity exercise, hydrogen gets to be very high from making too much lactic acid. It's also inhibited during moderate intensity activity like jogging and those kinds of things. PFK activity is as high as it's going to get. Okay. So here's how we're just adjusting. What are we dumping into these pathways? What are we moving through there? So now we've got more and more pyruvate getting pushed down into this area. And so we're then left with our two enzymes that control the fate of pyruvate. We have lactate dehydrogenase, which drives pyruvate to lactate. And then we have pyruvate dehydrogenase, or PDH, that drives it into acetyl-CoA and puts it into the Krebs cycle. Okay. And so part of these two, they're not particularly allosteric. Okay. PDH a little bit more so. LDH is mostly its activity is dependent upon fiber type. Okay. In fast switch fibers, LDH is more active. In slow twitch fibers, LDH is less active. So if you have a lot of fast switch fibers, you're going to make more lactic acid, which can be a bad thing, than if you have more slow twitch fibers. Okay. PDH, on the other hand, can be activated by ADP. It's largely inhibited by the presence of high levels of glycogen and high levels of free fatty acids. Okay. The free fatty acids inhibit it because if you've got a bunch of free fatty acids, that's what the Krebs cycle is using is those fat molecules to derive energy. So we don't need to break down carbs. So if you don't want to burn carbs, eat a bunch of fat. I'm not advocating for the Atkins diet or anything else necessarily. Okay, but metabolically, that's kind of where that flexibility is going to come. Okay, so this is controlling glycolysis. Right, ADP levels rise as we break down more ATP. We push more glucose in. We push more of that glucose that's gotten into pyruvate, and then we're left figuring out: is it going to lactic acid or is it going to Krebs? Okay. So I know that I said that PFK is the rate limited enzyme, but the big thing that controls the fate of pyruvate in so many ways, okay, is really going to be sort of this piece right here. The rate of our ability to push the pyruvate either into lactate and lactic acid or to fit it into the Krebs cycle. Because the front part, more glucose in, making more pyruvate, this piece is going to get stimulated and it's going to go way up during exercise no matter what. But the big issue that's going to control how you manage things during exercise, can you keep that pace up, is what happens here. Okay? So I want to point it out again. Glycolysis is not stimulated or inhibited by anything to do with oxygen. Okay? Carbohydrate metabolism is governed by these enzymes. It has nothing to do with oxygen. Okay? So the big pinch point that we're going to run into, okay, in why we get more lactic acid or more going to the Krebs cycle, realistically is going to come down to, okay, how much pyruvate am I making versus how much can the mitochondria take in and actually begin to break down. Okay, so there's a balance that's going to go on here. As I make more and more pyruvate, okay, in a general sense, PDH is a more active enzyme than LDH. So for any pyruvate that you're getting, the preference and the sort of biochemical underpinnings is that most of it's going to try to get dumped into the Krebs cycle. Okay, because PDH is more active than LDH. But if I make a bunch of pyruvate and I begin to swamp the ability of PDH to drive it into the Krebs cycle, then I will begin to make lactic acid. Okay, because it hangs around, it eventually interacts with LDH, and we make lactic acid. Okay. So there's two circumstances when this tends to be the case. Okay, when mitochondria cannot handle all of the pyruvate. There's really two things that are going to happen. Okay, one is at the onset of exercise, because it's going to take a few minutes for PDH to get fully activated, the mitochondria to get fully activated. And so early on in a bout of exercise, even if it's not that high intensity, you're going to make a little bit more lactic acid than you would later on. And the real instance is when it tends to predominate is at very high levels of intensity. We make so much pyruvate that we're going to have to make some lactic acid. There's so much getting dumped in from glycogen and the breakdown. There's lots and lots of pyruvate, so more of it's going to go that way. Okay. And then the problem is you make hydrogen, hydrogen inhibits everything, and the whole deal gets shut down. Okay. Okay. Now we'll talk about the one that is less interesting and in some ways we have less control over. And that's going to be aerobic or oxidative metabolism. The real thing that controls this is going to be the rate of the electron transport chain and the rate of the Krebs cycle. Okay. The primary thing that controls aerobic metabolism is the speed of the electron transport chain. Because Krebs is generally pretty fast, and Krebs can only go as fast as the electron transport chain can recycle the electron carriers to it. Okay. So at rest, the electron transport chain is generally inhibited. It's inhibited by high levels of ATP. Okay. So it's at its slowest rate at rest. Like everything else, when you turn over ATP, you make ADP, that begins to activate the electron transport chain. And that's going to lead to then our increased need for oxygen. Okay. So that's where this increase in oxygen consumption, this increase for O2 demand comes from. It's because we speed up the rate of the electron transport chain, so we need more oxygen as the final electron. Okay. So that's the big thing. It's primarily controlled by ADP and ATP. Okay. Krebs cycle, enzymes work well. You've got plenty of pyruvate coming in for the most part. The big issue that controls Krebs is just our ability to recycle NAD and FAD from the electron transport chain. Okay. That's the big rate, the way that we're going to end up controlling most of this. Okay. All right. During sub-maximal exercise, aerobic exercise is generally not governed by our ability to get oxygen. It's very rare, but in some instances, a lack of oxygen to be the final electron acceptor can slow down or be the limiting factor in metabolism. But for most of us, in most instances, that's rarely ever holding. The big thing, okay, the big thing, if you want to derive more energy from aerobic metabolism, make less lactic acid, use less creatine phosphate, make all of this work better, the single biggest thing that we can do is have more mitochondria. Okay? Have more mitochondria. If you have more mitochondria, there's more places for the pyruvate to go. You can put more pyruvate in if there's more mitochondria. Okay. It's just like football stadium. If there's more seats in the stadium, you can put more folks in. Okay. So by having more mitochondria, that's the biggest way that we do these things. Having more mitochondria actually speeds up aerobic metabolism because it makes us more sensitive. Okay. So how do we get more mitochondria? One, have more slow twitch fibers. You don't have a lot of control over that. Two, train aerobically. Do aerobic training and make new mitochondria. Okay. When you have more mitochondria, that's going to ramp those kinds of things up. That's going to be the big thing. Okay, so this is just a list of the rate limiting enzymes. And I'll leave you guys with this last little bit here, okay? This is showing the relative percentage of energy provided from aerobic and anaerobic pathways, okay? From completely anaerobic all the way to essentially completely aerobic. And then here on this list, this has time, and then it has individual sorts of swarming events and things that you might want to think about as we look back there. 1 to 3 or 5 seconds, it's basically entirely anaerobic because it takes us a few seconds to start pushing glucose and pyruvate in and ramp that up. Okay. Things that last for a very, very long time. Essentially anything that lasts more than about 5 to 8 minutes is going to be primarily anaerobic. Okay. Anything that is in there is mostly anaerobic. Okay. You can look at kind of how we're going to break down the sort of swarming events. All right. So when you go and you lift weights, it's basically an entirely anaerobic experience when you're doing that. You run a marathon. I don't know why you would want to run a marathon, but if you did, right, it's almost entirely anaerobic. Joe, you had a question. You look very, very, very quizzical about something.
For anaerobic, why is basketball and baseball? Like basketball, you run like a lot. So why is it 90% anaerobic?
Describe the running in basketball.
Exactly. Just like
Do you get to stop?
Sometimes no.
Come on. Sprint, you get to set for a couple of seconds, right? And then you walk, and then you jog, and then you sprint, and then you do those things. It's an intermittent sport, right? You're doing things for a long time, but it's very burst, rest. And by rest, I may mean jog or something like all of that, right? It is intermittent, okay? Soccer is another kind of interesting thing depending upon how you play, but it's a lot of walk, jog, sprint, walk, jog, sprint, fake an injury. Okay. One of my master's students that graduated this semester, she is a data scientist now with Miami SC. It's where Lionel Messi plays, the team that David Beckham owns. And for her master's thesis, we got to see all of their tracking data during their games. And you can see how often like they sprint at certain levels, how often they spend essentially walking or standing still and things. And it's a tremendous amount of time not doing anything or not doing very high intensity things. But it's like sprint, stop. And you may sprint for 20 or 30 seconds or something, but then you stop and you rest because the ball goes up, or you fake an injury. That's how this is going to work. So watch a basketball game and watch how much time they actually spend sprinting. Okay. I'm not saying it's not like metabolically taxing because it's long, right? sprint, stop, it's interval training, right? You can burn a lot of them, and it's very taxing. You have to be in good aerobic shape. All right, this is not going to be on the test, but I'll tell you guys this now, okay? These things that seem primarily anaerobic, okay, that seem and feel primarily anaerobic, you need to be in very, very good aerobic metabolic shape, if you will, to do these things, right? Because if you're not, you cannot recover in those little rest periods that you get. You cannot recover clear lactate, clear lactic acid, resynthesized creatine phosphate. Okay. That's one of the primary things. Why, if you're going to be a basketball player or a soccer player or anything where you do these kind of intermittent things that last for a while, you've got to be very, very highly aerobically trained so you can recover. It's much more about recovery than it is about the actual thing that you do in your little high intensity rounds. Okay. I will probably ask something on the test, give you a couple of sort of things like this, and ask you to do all of that. Okay, pick out like what's the primary energy system. But maybe I'll do a confusing thing, and I'll say like, okay, let's do this. Landon, you want to do me a favor? Sure. Walk down the stairs and then walk back to your desk. That took about 10 seconds, maybe. So what was his primary energy system? Aerobic. Okay. What do you guys think? Somebody said phosphagen, somebody said aerobic. It's one of those. Which one is it? Right, I mean, the honest answer is it was both. The first like couple of steps were probably mostly phosphagen, but you got to remember, right? The time component also in many instances denotes an energy expenditure and an intensity. If all I do is walk very slowly for a very short period of time, that's not a very high intensity, right? So I'm likely going to be able to mostly do that with aerobic metabolism. The reason that we say that things like weightlifting or 100-meter dash or doing gymnastics or something, right? It's high intensity and it's short because that's all you've got the energy to do, right? So you've got to consider both of those things, right? You can't all out sprint for 30 minutes because you just can't fucking do that. Like that's not a thing that you can do. To go that long, it has to be aerobic. It's got to be slow enough. But on the short end, you got to be careful. Okay, you got to be careful. So I can be tricky with all of them. All right. Okay. So that's sort of where we are. We've got, I don't know, 15 minutes or so left. You guys want to ask some questions? Yes, Matt.
Okay, so I'm just going to like the possible short answers.
Oh gosh. Okay.
There's a lot of them in the resistance training where it talks about like basically with initial signaling molecules processes. I know like you mainly talk about mTOR.
Yes.
Throughout those lectures. With those, you're talking more about like translation, transcription as well, kind of like implementing those as well in our answers, or just mainly focusing on mTOR pretty much.
Mostly mTOR. So
Gotcha.
mostly mTOR, right? mTOR drives the transcription, which then drives the translation, right? Now, how do we activate mTOR? Okay, yes. Can we be more specific? You would never go walk and think you're going to activate mTOR, right?
Resistance training.
Okay, good. What is it about resistance training specifically? What makes resistance training different than walking? Pardon? Mechanical stress. Okay. How do I get mechanical stress? More weight, more load, or lengthening. I need lengthening. I need the stress, right? I want to do that. I can even do that by increasing load. What else though? Do I have to lift a heavy weight to get hypertrophy? I have to go to failure. Okay. So clearly there's something about failure that gets me a similar amount of mechanical stress regardless of how much weight I'm lifting. Okay. But we haven't talked about that. It's a little bit more advanced. But the big thing is it's your type 2X fibers that are the ones that you never use, or the ones that have the greatest capacity to grow because you don't ever use them. And you need to recruit them. And if you use a lightweight, you got to do a bunch of reps before you fatigue enough that you'll actually use them. If you use a heavier weight, you tend to have to use them sooner. And so that's why getting to failure means you've likely used those last 2A and 2X motor units that you don't normally ever engage that have the greatest capacity to grow. Okay, that's how all of that works. We activate mTOR with stretch and load. That load gets us mechanical stress. The stretch gets us mechanical stress. So how do I get stretch during exercise? A full range of motion. You're close, Nathan, but you're not 100% there.
What's the language during the eccentric phase, right?
Eccentrics. Okay. Concentric, eccentric. Don't just drop that weight when you're doing the eccentric portion. And for most of you guys, when you go and work out, right, like you've got to do Con-Ec anyway. Right? If you don't have a partner, you're going to do a squat, you have to stretch to go down. Like there's no way to avoid all of that. Okay. But they do make some machines and some things, sometimes from a rehab standpoint, you can isolate and just do the concentric portion. We know that if you do Con-Ec, you get more hypertrophy than if you do concentric only. Problem is nobody ever really does concentric only. Anybody ever, so complete aside, there's something magic about stretch. Anybody ever been in a cast? Okay. Kevin, what were you in a cast for?
I broke my wrist.
You broke your wrist. Never mind. Okay. That's not as noticeable in that particular way. Okay. Anybody else? Anybody like break a leg or an arm or something? Audrey, what'd you break?
I have tibia.
Broke your tibia.
Ankle.
Did they cast you with your like in plantar flexion or dorsiflexion? In plantar flexion. So like this. Okay. Out. When we cast a muscle, so in doing plantar flexion, which muscles are shortened and which muscle is the most stretched? Gastroc and soleus are shortened. TA, don't gotta be impressed, I know that. TA, stretched. When you were that way, did your gastroc and soleus shrink up like nobody's business? If we had looked at your TA, it would not have really gotten any smaller. When you get casted or do something, the muscle that's casted in a stretch position does not atrophy. Or if it atrophies only a tiny amount. The ones casted in a shortened position atrophy like nobody's business. There's something magic about stretch. Okay. Something magic about stretch. We tried when I was a PhD student to overstretch muscles. We'd have people come in and we put them in a boot and we crank it down and we try to stretch their calf. We tried to train them by stretching to see if we could make their muscles get bigger. We couldn't. The stretch by itself doesn't really work if you're getting normal activity, but it will prevent atrophy. Okay. In the same way that doing blood flow occlusion and also putting people in a hot tub or a sauna also seems to prevent some atrophy. So we can, there's lots of different weird mechanisms. Anyway, we've gotten very far afield. Matt.
Can we discuss genetic limiters for hypertrophy? Because I know we talked a little bit about like how.
Yes, we can discuss them. Someone give us one. How much myostatin? More good, more bad for hypertrophy? More bad. Okay. The more myostatin you have, the likelihood is you're going to be less of a responder. Okay. That's one. Somebody give me another one. I know some of y'all know because you come to my office and ask me about it. So share. Number of muscle fibers. Why do you think that matters, Joe? Correct. But that still doesn't say like why Why would the number that I have be of any level of importance for how much bigger they can get? You gotta be more specific. So what is, What is it?
You have more smaller muscle fibers that have more capacity to grow.
yes. Yes. You have many small fibers to start with. Okay, now that only works if you have potentially that in combination with one other thing. It is going to be a genetic thing. You want to have many small fibers. What's the thing that puts the limit on how big the fibers can get? Satellite cells, which become nuclei. Okay. You ideally, if you want to be a responder, want to have many small fibers to start with. You'd like to have a lot of myonuclei to begin with. And for sure, you want to make sure that you have a large number of satellite cells that you can then incorporate as those fibers grow. Because remember, growth is limited by our ability to keep the ratio of myonuclei to fiber size constant. The fiber gets too big, right? And there's not enough myonuclei, it will not be able to get any bigger. So, myostatin, many small fibers to start with, many myonuclei, many satellite cells. Those are all things that can play a role. Anything else? None of the questions are like 3. You know, like, nope, we all got these. But I might ask you something else in a.
We can talk about like how genetically receptive you are to those anabolic hormones to a degree.
Sure. How would we determine how genetically receptive I am? What does that mean?
Like how sensitive those receptors are, I guess.
Okay. I saw a crazy Instagram reel that was like, as you age like I am, that you become anabolically resistant. And I'm like, this is just completely wrong. It's a guy in his scrubs claiming to be a doctor. And I'm like, nope, not true. Not true. Like you stop having an ability to respond to exercise as you age. And I'm like, nope, not true. It's completely false. They were, of course, trying to sell some kind of a supplement that would make you more receptive. But the bigger issue is probably not how receptive you are to the anabolic stimulus. It's probably just baseline levels of, are you kind of higher or lower on the spectrum of primarily testosterone? Okay. It's going to be in there. Testosterone and growth hormone. There's some genetic variation in all of that, just at rest within kind of normal physiological reasons. You would like to be on the higher end of all of that if you want to be a good responder. Joe.
You explain what signals from exercise push muscle fibers into the state of positive protein balance?
We already did. mTOR. mTOR, 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 mTOR. And how do we activate mTOR? Yes. Load, stretch, failure. Right. Yeah.
So, the question that asks how to like make a resistance training program for our friend, would we say that we would just put them to failure,
Yes.
or
Doesn't matter what we're doing, go to failure. Whatever
6
muscle,
months of failure?
yes, whatever muscle group you want to make bigger, failure. Now, it's likely a little bit more complicated, right? Because you could say, if they've never done it before, like 1 set of 10 reps a week to failure is going to be fine to start with. As you become a little more advanced, you probably need, right, maybe 2 sets or 3 sets in a second day per week. But generally, failure. How do we get failure? Overload, right? How do we get overload? Well, when it becomes easy, make it harder. Do more reps, do more weights. And it's absolute most basic, yes, failure. Okay. Now, if you just simply train to failure like 6 times a week for 6 months, you may be a very unhappy trainer. Okay. We haven't talked at all about recovery. We haven't talked about overtraining at all in those ways, but there's a lot of, that's where a lot of the kind of the newish science is how do we optimize kind of what that How often should we go to failure? How often should we do other things around that? Okay. You might also want to say they should be doing concentric eccentric, right? Big muscle group, concentric eccentric, go to failure. When it becomes easy, make it hard. You're now better at resistance training programming in 30 seconds than 90% of the people in the entire world. And this is why we make you all take health promotion classes. None of us actually want to do that. Right? It's a behavior. The biggest thing is people won't go. It's not that hard. I mean, it is hard, but what to do is not that hard. It's not that complicated. None of us want to go, or we don't have time or something, right? I was watching soccer Saturday morning, and I was trying to do squats and push-ups in my floor, and my daughter keeps bothering me. And I'm like, damn it, I'm just trying to like do one thing. So I got her, and she got and laid on my back while I was trying to do push-ups, which made the failure come much, much sooner on those things. She was like, Daddy, you're not very strong. And I'm like, I know. Anyway, there was another question. We got a couple of minutes left, guys. So there was another question somewhere. Matt.
Okay, two phases of pyruvate.
Yes.
Talking about advantages, disadvantages, I get like lactic acid pretty much, that's gonna cause hydrogen to increase, which is gonna inhibit the whole system pretty much.
Yes.
Is there an inherent disadvantage to the Krebs cycle though?
Is there an advantage to the Krebs cycle?
No disadvantage?
No.
Okay,
No.
That's part that's.
There are no disadvantages to aerobic metabolism. There's only good from aerobic metabolism. There's no downside. Okay? You do not make anything that causes fatigue. Okay? There's no downside. You make more energy and it doesn't inhibit things.
That's it.
I didn't put it on the thing. If I made you pick, this will not be on the test, but if I made you pick metabolize fat or metabolize carbohydrate, what should be the preference? Fat. Always fat. Why? No downside. No downside to fat. Carbs could go to lactic acid. Okay? There's no downside to fat. You can't always do that, but there's no downside to it. Okay? What's the other questions? Victor.
So citric acid is produced by the Krebs cycle.
Yes.
So why is lactic acid
It
bad?
stays in the mitochondria. The hydrogens stay in the mitochondria. The hydrogens get out of the mitochondria and get into where they can interact with, right, myosin and the calcium ATPase and those sorts of things. They can interact with the enzymes in the glycolysis enzymes. Then we get problems. But that's the big issue. Most of those hydrogens just get shuttled around and we use them in the gradient to make ATP. So, but a very clever question. I will be around the rest of today. I should be in the office most of the day tomorrow. If you have questions, come and see me. Okay? All right. See y'all Wednesday. I'll try to be here again at like 8:30. I'll be started.
Keeping in the loop, my dad left out of town. It's not happening, people, but I can't be fine for the rest.